Well, we're going to now look at homogeneous linear differential equations with constant coefficients. What do you think? You ready?
I'm ready for something.
Okay, I hope this qualifies, but I guess we'll have to wait and see. First of all, the discussion is about second order, but we could actually apply the technique for higher orders than that, so it doesn't have to stick with first order equations. Anyway, second order homogeneous linear differential equation with constant coefficients would look like a times y double prime plus b times y prime plus c times y equals 0. If we were to guess at a form for a solution, a good guess might be y equals e to the m times x for some value of m. Does that make sense? I hope so. So here's the story. If we assume a solution of that form, then y prime, of course, would be equal to m times e to the mx. And y double prime would be m squared times e to the mx. And so, if we substitute back into the equation, we got a m squared e to the mx plus b m times e to the mx plus c times e to the mx equal to 0. So, I don't know if you see where this is going, but it's going to a nice place, because if we divide out by the e to the mx, it gives us what's called the characteristic equation for this differential equation, and it's just a quadratic equation in m. am squared plus bm plus c equals 0. So easy to solve that. Sometimes they'll factor, but I don't know. Will this one factor?
I really don't know.
No, of course you don't know, because we don't know the value of a, b, and c. So we'll eventually look at some examples. Anyway, what's called the characteristic equation of a differential equation of this one is am squared plus bm plus c equals 0. Be careful, later you're going to see some other types of characteristic equations, but for a linear second order, that will always be our characteristic equation. So there are three cases for such a quadratic equation, as you may know from algebra. And one case is they're both real numbers, the roots are real and distinct, and for what it's worth, I know that happens about 65% of the time. So if that's the case, then our general solution is constant 1 times e to the m1 of x plus constant 2 times e to the m2 of x. And isn't that wonderful how that works out?
I sincerely hope so.
Yes, it is. So what if there is a single repeated root for the characteristic equation, called a double root? In other words, what if it's a perfect square? In that case, the solution is c1 times e to the mx plus c2 times x times e to the mx, and we could go through the reduction of order. Actually, you could go through reduction of order from the last lesson, Unit 3, Lesson 1, or if you wanted to see a little bit better version of that, see Unit 3, Lesson 3, Case 2 for something similar. But that would work, and it would be no problem. Now, here's where it gets tricky. Suppose your solution is a pair of complex conjugates. In this case, let's say a plus or minus bi are the solutions. Then we could write, but it would be extremely nasty, we could write y is c1 times e to the a plus bix plus c2 times e to the a minus bix. But that's not too simple. We got imaginary numbers as exponents, and not very many physical things in the world are going to really work nicely like that. So, yeah, we need a little help with this. So, is there a way we know of to use things we know already to eliminate this difficulty?
I sincerely hope so.
Yes, and there is. And here's the trick. I want you to recall what was called the Euler formula, one of the most beautiful formula in all of mathematics, as I've been told by many other people. It's e to the I theta is cosine theta plus I times the sine of theta. And the Euler formula can be derived, if you can't remember doing it, from the Maclaurin series, and I'm sure I'd be glad to make that a homework problem. But it's pretty easy to do that. You have to look up the Maclaurin series for cosine and sine and e to the x, and when you do that, it'll be very apparent and it'll fall out quite easily. Anyway, if we do that, then we can see this y now can be written as you know, the rule for e to the exponents here, c1 times e to the ax times e to the ibx plus c2 times e to the ax times e to the ibx, negative ibx, that's right, plus or minus. And so we can factor this e to the ax out, and this e to the ibx and e to the negative ibx, trust me, you would wind up with cosine bx plus I times the sine of bx. And yeah, I know that's really only this one, so let's put the other one out there too. C2 times, be careful about all my parentheses, I hope I have enough here. I'm not sure that, yes I do, no I don't. I really need another parentheses to cover, or maybe I just need to drop this one off. Yes, I feel better now. Yes, that's good. I just had a parentheses in the wrong spot there. So here's this has already been factored, this e to the ax has already been factored out, and so then I have c2 times e to the negative ibx, which is here. Whew. Or, okay, more simply, y equals e to the ax times c1 plus c2 times cosine of bx. See, c1 cosine of bx. Here's got my capitals and smalls mixed up here, so bear with me as I try to resolve my typo here, my gaffe. Okay, I have these small letters everywhere, so make this one a small and this one a small. And I hate it when that happens, when I'm typing something and it kind of goes, hey, my computer kind of goes haywire. There we go, haywire again. And I've lost my place, but I'm almost, there we go, cosine of bx, now I've got it. Lost it again. Okay, this is what I wanted to say. This is e to the ax times c1 plus c2 cosine of bx. See, cosine of bx here, cosine of bx here, and that should be wonderful. You should see that without a problem. And then c1 minus c2 times I times sine of bx. See, c1 times I, whoa, sine of bx, what happened there? Something goofy. There, that's what I wanted. So c1 times I times sine of bx plus, or minus c2 times I sine of bx, see it? So there's all that. And you're thinking, but c1 plus c2 as well as c1 minus c2i are arbitrary constants. So I'll just call them capital C1 and capital C2, and with that we get our general solution without imaginary exponentials. Y equals e to the ax times constant times cosine of bx plus some other constant times the sine of bx. And the imaginary number of solutions of, the imaginaries would be taken care of by the constants, but they're arbitrary, so we don't care. And we're very happy that we don't have imaginary exponents. Whew.
Ooh, that's hard. So very difficult.
Yes, it is, but I think we got it. So we'll do some easy ones in the next video.